Okay. So just like we watched the video yesterday, right, on ancient chemists, and that just kind of introduced atomic theory. Now, this unit is theory, so it's a lot of just information. We're going to be looking at experiments that scientists did, what information that gave us about the atom, how we modified atomic theory over the years. So like any theory, you can modify any theory once you get new information, right? So with atoms, it kind of goes along with technology. The more technology we have, the more we can learn about an atom. And therefore we modify our previous theory to kind of put our new information in there, right? So we started off with just an idea. Do you remember who they said on the video gave us the first atomic idea?
Yes.
Democritus, right? Close enough. So this unit is atomic theory. Okay, so Democritus gave us the first atomic idea. We can't call it a theory because in 400 BC, there wasn't a whole lot of technology around, right? So we didn't really have any proof. So basically what Democritus, he just thought about this, right? It was just an idea. He didn't have any evidence. It was just, people were just sitting around thinking about stuff like, oh, I wonder what makes stuff up. And he thought, well, I think that if you keep dividing matter down, you're eventually going to reach a small piece that you can't break down any further, okay? And he called these pieces atomos, okay? He called them atomos, and that's where the term atom. This was in about 400 BC. Okay, we just have approximate dates. So around 400 BC is when Democritus came up with this idea that atoms exist. And on that sample slide that I gave you for that book or Google slide thing that you're going to do with all the different scientists, the analogy they gave for modern day analogy to kind of think of what he was thinking of would be Legos. Because he was just thinking that atoms were different sizes and shapes to represent different elements or different substances, and that they just linked together to form other things. Sort of like Legos, you can put different size Legos together to build something bigger. That's kind of his idea of what atoms were. Now, obviously, there were no Legos around in 400 BC. That's just our modern day analogy of what he was kind of thinking. What's that? Oh, linking logs. 400 BC. All right, the opposing views at that time came from where? Who had opposing?
Plato.
Right.
Oh.
I can spell it. Yeah, it was Plato and Aristotle. I think Aristotle was Plato's student or something, is that right? Okay. So they didn't think along the same lines of Democritus. And at that time, it was really just whoever was more popular, that's who people followed and said, yeah, I like your idea better. And kind of went with that. So they were actually trying to get all of Democritus's stuff banished, like taken away, because it didn't agree with their idea at the time. So they thought that matter was continuous. I'm not reading well at all. That's supposed to be matter. Matter is continuous. So that was the opposing view at the time, and most people kind of followed that view because they were the more popular philosophers at the time. So, and we didn't have any evidence to back anything up, so therefore just kind of followed whatever they say. So does that make sense? So the analogy there is kind of like Legos. If you think of atoms as being Legos, are different sizes and shapes, and they can just kind of stick them together in different ways to make other things. But like I said, this was a philosophy. 400 BC, there really wasn't any real technology that we could use to get the existence of atoms. Does anybody know who came up with the first atomic theory then? This was just the idea. This was kind of like our starting point. Nope. It was much later. These guys were already dead and gone for lots of years.
Albert
No, he does come into play as we started to modify it. Did you ever hear of John Dalton?
No. Oh, we talked John Travolta. Right. John, stay long.
All right, so John Dalton, in English, he was an English scientist and school teacher. He was actually. And this was, I'm not going to make you memorize dates. I'm just putting them out there so that you kind of get a reference of time, like how much time went by. But this, he stated the first atomic theory. So he actually had evidence now where he could state and back it up with evidence that atoms existed. Okay. Now there's 5 parts to his original theory, and then he also modified it and put a 6th part. So we're just going to go through those together. Okay. How are your chromatographies coming along? Are they getting close to the stick? Okay, when it gets really close to the stick, let me know and we'll pause and I'll let you take it out and put it off to the side and then we'll keep going. Okay, what you'll want to do when that chromatography gets up near the top, you want to get a piece of paper towel, just fold the paper towel and put it on the paper towel. You put your name on the paper towel and you want to put pencil marks where the water went to, and you want to put pencil marks where at the top of each color that you see. And the reason it's important to put pencil marks on right away is it's going to keep moving even when you put it on the paper towel because it's still wet. And you want to know where your original marks were. It's really important to know where your water stopped and where the pigments were at the time. So you just have to put those pencil marks on. All right, see, it only took 2,200 years, right, to go from the first atomic idea until we actually had evidence that the atom existed. So all this time went by, right? Over 2,000 years go by until we finally have some evidence that the atom existed. But what you're going to see now is it's going to just be like boom, 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 boom. Like we're going to keep making discoveries in a really short period of time, because once we got the evidence, that makes people curious and they want to know more, right? They want to know more about stuff.
Sorry.
Let me actually spell words correctly. He has 5 original parts, and then he's going to add a 6th part to it. Okay. I want to make sure I'm writing this down the same way I did the other class. I took a picture of my masterpiece. So the first thing he stated is basically what Aristotle, or what Democritus, what Democritus's idea was, that all matter is composed of extremely small particles called atoms. So he kept that name, the atomos name, and incorporated that into his theory. Okay, so all matter is composed of extremely small particles called atoms. That's the first part. And then the second part was atoms of the same element are identical and by identical we mean by size, shape, mass. So they're identical in every way. Okay, so atoms of the same element are identical, and atoms of different elements So atoms of the same element are all identical in every way. But if you have two different elements, those atoms have to be different. They can't be the same size, shape, all that kind of stuff. So atoms of different elements are different. I think so.
Yeah, he was sitting in your bed. Emily.
Atoms cannot be destroyed, created, or subdivided. Okay, atoms cannot be destroyed, created, or subdivided. What law does this kind of resemble, especially the first part of it, that atoms cannot be destroyed or created? Anybody know what law that? And it's energy and matter it deals with. So what is that? It's law of what? Of energy and matter. This in one term. Anybody know? Where we say we can't destroy or create things. What's that? On the right track. It's don't you love that squeak? So law of conservation of matter. Now, there is a law of conservation of energy as well. He was only talking about matter here, but the energy part is actually going to come into play as we develop the atomic theory a little bit. That's where Einstein came into play, because he realized that matter and energy can be interchanged. So he was able to state this. I want you to keep in mind too that he didn't really do the experiments himself. He was taking other people's experiments that they were publishing and getting that information and kind of putting it into a theory. Does that make sense? So he wasn't the one like doing all these experiments, but he was the one that was kind of saying, hey, this proves this, and he just kind of put it all together. What was a big deal at that time, which doesn't seem like a big deal now, is they were carrying out experiments in a closed system at this time. So like when you burn something, it looks like it just disappears, right? And people didn't know what was happening to the substance. Like if you went through a chemical reaction, like burning or combustion, they didn't know what was happening to the stuff. Like it looked like it just disappeared, right? They didn't realize that these invisible gases were being formed and just kind of going away into the atmosphere. Once they started to do experiments in a closed system, then they could tell that, you know what, the overall mass is still the same. It didn't go anywhere. It must just be turning into something we can't see that's still in that system. So that's where this came from. It was kind of a big deal at that time because they were discovering, you know, that, oh, it does just form other stuff, and we have the same overall mass in the end that we had in the beginning, okay, which brings us to the next part of history.
Would it be turned into gas? If it's like
What's that?
burned, if it's like burned, would it be turned into gas?
Yeah, you part of it is turned into gas, some of it's like carbon. So. Okay, so along with this, and kind of goes along with the law of conservation of matter. Okay, give me 1 second.
There's a barcode. I'm like, please try that. I got that.
Okay, so the next part of this, then, he's talking about what atoms actually do. When there's a chemical reaction that's taking place. Okay, so when he would see chemical reactions, or when scientists would see chemical reactions taking place, this also goes along with the law of conservation of matter, right? This kind of, both of these combined kind of exemplify the law of conservation of matter. So what he's saying is what's actually happening in a chemical reaction is the atoms that are there are still there. They're just separating from each other or combining together in different ways or rearranging themselves. We're going to talk about all different kinds of chemical reactions as we go through the year. Okay, but atoms combine, separate, or rearrange in chemical reactions. So that's what's happening at the atomic level with chemical reactions. Okay. And then the last thing he stated, now I'm going a little out of order than what's in your textbook because these two things go together. So I like to put them together. Right. So the other thing he stated, in order to form compounds, the way we get compounds is atoms combine in simple whole number ratios. Sorry, my handwriting gets worse as I get lower. Atoms combine in simple whole number ratios to form compounds. So atoms combine in simple whole number ratios to form compounds. Now there's another law that this exemplifies. Called the law of definite composition. Okay. So atoms combine in simple whole number ratios to form compounds. And this exemplifies what we call the law of definite composition. Does anybody know what that law is? What that means? Okay, so when you think of water, what do you know that water is made of? Hydrogen and oxygen. And do they come together in any specific ratio when they come together? Right, 2 hydrogens for every 1 oxygen, right? And that's always the case for water. It doesn't matter if we get water out of the spigot, out of a pond, out of the ocean, out of the glacier. Okay, it's always 2 hydrogens to 1 oxygen. That's what the definite composition means. Okay, so that a compound has the same composition regardless of sample size or source. Okay, so like if we have water, it doesn't matter if I get water, if I have a pot of water or a glass of water or a drop of water, it's always going to have that same composition and ratio, right? 2 hydrogens to 1 oxygen. Okay, I'm going to pause there a little
Yeah,
bit.
don't erase that. Why are you walking like that?
All right, so then what was happening here when he realized that atoms came together in ratios to form compounds, at that time they thought that they always came together in the same ratio. Like if hydrogen and oxygen were going to come together, they were always come together in 2 to 1. But they realized later that actually 2 elements can come together in different ratios. But when they do, they form completely different compounds. So his 6th, this is the one he added later. I think it was around 1809 or 1810. It was very close to when he did his original theory. He just got a little bit more information and added it to it. That atoms can combine in different ratios to form different compounds. Okay. So atoms can combine in different ratios. The same atoms can combine in different ratios to form different compounds. And this is known as the law of multiple proportions. And this is known as the law of multiple proportions. So this is where that, I don't know if you ever heard the one joke where 2 guys go into a restaurant, they sit down at a table, the waiter comes over, asks them what they want to drink. First guy says, I'll have some H2O. Second guy says, I'll have some H2O2. And he dies.
Rookie mistake.
Why is that?
H2O2 or something else. More oxygen.
So there's H2O, H2O2, definitely not the same stuff, right? This is water, obviously. Does anybody know what this is, what this substance is?
Something bad.
It is, although you can buy it in the grocery store. It's just very, very, very diluted. It's a very diluted form in the grocery store. Some people put it on cuts. Not acetone, hydrogen peroxide. So hydrogen peroxide is very unstable. The stuff you buy in the grocery store, I think it's like maybe 2% or 3%, something like that. So there's very little hydrogen peroxide. It's mostly water. It's very diluted. It's also very unstable, which is why they put it in brown bottles, because sunlight itself will break it down. When it breaks down, it actually breaks down into H2O and oxygen. Okay. So if you have hydrogen peroxide laying around too long, it's probably just water in your bottle because it probably all broke down. It also has, if you have a strong solution of it, it has to be shipped in a accordion bottle that can stretch, because if it reacts very quickly and it forms that oxygen very fast, and you don't want your bottle to explode. So it's like an accordion bottle that if it happens to react in shipping, it's just going to expand your bottle and it won't explode all over the place. It's also very dangerous because it forms pure oxygen very quickly. So if there's anything around it that's combustible, oxygen feeds fires, right? So if you're producing pure oxygen very quickly and there's something nearby that combusts very easily, you're going to start a fire. So hydrogen peroxide is not stuff to mess around with. Like I said, the grocery store is like a 2% solution of it. The stuff they use to bleach your hair is actually hydrogen peroxide. That's like an 8% solution.
Is that why they say that like you can use like hydrogen peroxide and brush your teeth with it? Like,
Yes, I think they put a little bit of hydrogen peroxide. It would be a very dilute.
I soak my retainers in hydrogen peroxide.
Right, because it'll kill bacteria and things like that as it reacts. Some people, did you ever put it on a cut and see it like? Yeah. So you don't ever want to put that on a really deep cut, because actually hydrogen peroxide is actually like cooking. Like if you put it on raw meat, it like cooks the meat. Basically, it's not cooking it, but it changes the protein structure, sort of like cooking it does. So if you have a deep cut and you start pouring hydrogen peroxide inside there, it's basically cooking you inside there. Like it's turning, it's changing your protein structure in your meat, your protein.
In my meat.
So, I mean, I don't know how else to say it, your whatever it is in there. So one time I caught myself when I was about your age. I worked at a fly store and I was stocking shelves and I had to use one of those box cutters to open up the boxes and it slipped. The best part was it was right in front of the deli. So it slipped and it cut me. I still have a scar there. Went right into me and the blood started to squirt out and it went all over the floor in front of the deli. That was the best part. And then they took me in the back room and they were gonna pour peroxide on it. Whoever was taking me in the back room to take care of it. Because it really opened up, like I went pretty deep in there. So I ended up having to go to the doctor and get stitches and all that kind of stuff. But, so you don't want to pour that kind of stuff in there, and because it'll actually create more damage. It's okay for small cuts because it kills the bacteria on the surface, but it's not good for deep cuts. You should never put it on cuts. All right. Any questions on that? Does everybody understand Dalton's atomic theory? All right. So that's as far as I'm going to go today with the atomic theory. The only thing that I wanted to add, every time we talk about a new scientist, we want to kind of look at what do we think the atom looks like based on their new addition to that. So his real world analogy is his atom looked like a billiard ball. Everybody knows what billiards are, right? Pool. Okay. So he just thought that the atoms were the smallest thing, that they were kind of like spherical in shape, maybe different sizes, that kind of stuff for different atoms. But you couldn't go any further than that, that once you hit that atom, that's as small as you could go. Now we know, of course, today we have subatomic particles, right? But at this time, we just were finding out that atoms exist. We have no idea that there was subatomic particles even smaller. So that's his model, that atoms are just kind of like little billiard balls, little tiny, ultra microscopic. All right. So we'll use the rest of the period then to analyze your chromatography.